Okay, this video is about the definition of a differentiable function of several variables. So, the definition of a differentiable function of several variables. And to introduce this, let's just review the definition in single variable calculus. So if you have a function, let's say from R to R, and A is some real number, then we say that f is differentiable at A if the limit as h goes to 0 of f of a plus h minus f of a over h exists. Okay, that's just a review. And if it exists, if this limit exists, we call it f prime of a, right? The derivative of f at a. Okay, and our goal is to generalize this concept of differentiability to just functions from Rn to Rm for any n and m. Okay, and so we have to give a definition, and we have to think about what do we want the definition to satisfy. So some things that we would want are that every differentiable function is continuous. Another one that we would want is that the composition of differentiable functions is differentiable. And we also want the properties of differentiable functions that you get in single variable calculus, like the chain rule, right? And in particular, we also want when n is equal to m is equal to 1, you want this to coincide with the definition above. Okay. So the first thing is, and this video is about leading up to the definition. The definition we gave above about this limit existing doesn't generalize well to higher dimensions. So the definition above does not easily extend to higher dimensions. So we need an alternate characterization of differentiability. So we will give a definition of differentiability which is not the one that we're used to, but that is equivalent to the definition above, and that does generalize. So the starting point is the following proposition, that f is differentiable at A if and only if there exists a real number d such that the limit as h goes to 0 of f of a plus h minus f of a minus d times h all over h is 0. So let's call this condition star, that there exists a d with this property. Okay, let's prove that these two are equivalent. So suppose that f is in fact differentiable at a. Well, in other words, f prime exists, so we have that the limit as h goes to 0 of f of a plus h minus f of a over h equals f prime of a. And then you just do some algebra, and then you get that this is the limit. This tells you that the limit of f of a plus h minus f of a minus f prime of a times h all over h is 0. Right? You just subtract f of a, you move it in the limit, multiply and divide by h. So the condition star holds with d equal to f prime of a. So that's one direction. Now conversely, suppose that star holds. Okay, well, if this star condition holds, we can just rewrite this limit as the limit of f of a plus h minus f of a over h minus d. Right, the limit of this is 0. And if you have, so d is some constant, and so you have this thing, that minus d is approaching 0. Well, the only way that can happen is if that thing approaches d. Okay, if you know, if you're not convinced, you can prove this using the formal definition of a limit. So this implies that the limit as h goes to 0 of f of a plus h minus f of a over h exists and equals d. And therefore, the limit exists. I mean, that's the definition of being differentiable in A, that this limit exists. Okay, so the n equals d is just parenthetical. So that completes the proof. So now we have a way of thinking of differentiability in terms of this criterion. Now this criterion is equivalent, so now we're ready to continue. This is equivalent, so that's the end of the proof. This is equivalent to this next condition that I'll write with 2 asterisks, which is that there exists d in R such that the limit as h goes to 0 of f of a plus h minus f of a minus d times h over h is 0, the absolute value of h. Okay, so the only difference between this and the one with that I had before, right, the only difference between this and this, and this is the absolute value of h on the bottom. But it's, okay, this is like an exercise that this limit is equal to 0 if and only if the other limit is equal to 0. Right? Because, you know, absolute value is just plus or minus h, and you just move the plus or minus to the other side. And okay, It's like an exercise. But this one is closer to the one we want, as we will see. Now we're ready for the next stage of generalizing this definition to higher dimensions, which is this d times h, right? This constant times h. So the idea is that that's a linear function of h, and when you have a function, so when you have a function from r to r, it's approximated by a linear function if it's differentiable, and the idea is that if you have a function from Rn to Rm, if that's differentiable, it should be approximated by a linear transformation, a linear mapping from Rn to Rm. So that leads us to the next stage. We're pretty much at the stage where we can just give the general definition, but let's just recall that every linear transformation t from r to r, oh, okay. I'm used to using t for transformation, but let's just use L because I'll use L later. L from r to r has the form h maps to d times h for some real number d. And so we have that a function from r to r is differentiable at A if and only if, okay, this next condition has 3 stars, there is a linear transformation L from r to r such that the limit as h goes to 0 of f of a plus h minus f of a minus L of h all over the absolute value of h is 0. Okay, this is equivalent to being differentiable at A. And roughly what this says is that near A, the function f is well approximated by the function L. In the sense that, you know, if you just didn't have this bottom part, right, the dividing by the absolute value of h, then if you just had this statement without the denominator, then that would hold for any function L with L of A equal to f of A. Is that right? Yeah, I mean, if you have, let's just do an example. Let's say that you had f of x equals sine of 2x. So that function looks like this. And, okay, let's look at the differentiability at a equals 0. Well, the linear function L of x, so f prime of 0 is 2, and so the linear function L is just L of x equals 2x. It's this, gives you the graph of this line. And since f of 0 is 0, then we just have the limit as h goes to 0 of f of h, right, so that's sine of 2h minus 2h over h is 0. That's what we get from the differentiability. So yeah, if you just somehow didn't have this h, right, then you could replace the 2h here with literally any number, and the limit would be true. I mean, we have that the limit as h goes to 0 of sine of 2h minus like 5h or any constant times h is also 0, right? But if you have this condition that it's not just that the difference approaches 0, but the difference divided by h approaches 0, then there is a unique number, right? The derivative is the unique number that satisfies this condition. Okay. So notice that now we're interpreting the 2, right? When we say that f prime of 0 is 2, which it is, you know, when you take a course in calculus, it's interpreted as, for instance, the slope of the tangent line. But now we don't want to think of this as the slope of the tangent line. We want to think of the derivative as it gives you a linear transformation that approximates the function. Okay? And it's actually this definition, or this criterion, this equivalent condition to being differentiable that does generalize easily. Because, right, this is from R1 to R1, and we have a notion of a linear transformation from Rn to Rm, and basically this, oh no, can I undo that? This absolute value of h will just get replaced by the magnitude of the vector h. So it is this characterization that is the characterization of differentiability that we seek. It's the one that we wanted to give us a general definition. So let's now give the general definition. So suppose that you have a function, and if I go from Rn to Rm in general, I'll usually denote the functions with a capital letter. So suppose that this is a function, okay, just any function, and any vector in Rn. We want to define what it means for f to be differentiable at A. We call f differentiable at A if there is a linear transformation L from Rn to Rm such that the limit as the vector h approaches the 0 vector of f of A plus h minus f of A minus L of h all over the magnitude of h approaches, well, if the limit is equal to the 0 vector. Okay, let's make a comment on the notation. So on the denominator, this is a scalar, right? Let's just remind ourselves that the vector h is, so this number, this is a real number, because if h is the vector with components h1 through hn, then the magnitude of h is the square root of h1 squared plus dot 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 plus hn squared. And here I have a function f from Rn, and the outputs are in Rm, and so A and H are in Rn, f of that's in Rm, f of A is in Rm, L of H is in Rm. So I have, so this numerator, right, this numerator is in Rm. And I'm saying that the limit of those vectors is the zero vector, right? When you scale by 1 over the magnitude of h. Okay, I don't think this is a very intuitive definition, so I wouldn't try to think too much about the intuition. But one indication that this is a good definition is that this, in fact, if n is 1 and m is 1, right, this definition does coincide with the definition of differentiable functions from R to R. So that's good, and we will see that actually if you have a differentiable function, it is continuous, and the composition of differentiable functions is differentiable, and they just have nice properties. Okay, so this linear transformation L, recall that if you have a linear transformation from Rn to Rm, it has a standard matrix, and so that leads us to this definition. Suppose that f from Rn to Rm is differentiable at A, the standard matrix of L, L being the linear transformation in the definition, is called the derivative of f at A. And this matrix is denoted df of A. So in the case where n and m are both 1, this is just a function from the reals to the reals, and you have a 1-by-1 matrix, and the number in the matrix is just the derivative, right? It's just f prime of A. And so this leaves us with several questions. For instance, you know, how do we describe this matrix df of A? That's something we haven't talked about, and we will talk about that later. Oh, and one more indication that this is a good definition is that if f itself is a linear function, then then the derivative is just itself. Okay, more precisely, let's say that f is a function from Rn to Rm defined by f of x equals b times x plus some vector b, where capital B is an m by n matrix, and lowercase b is some vector in Rm. Okay. So in the case where n and m are 1, this would just be like, you know, f of x equals mx plus b, right? Then we claim that the derivative of capital F is in fact b for all x. So, well, let's see what happens. So f of x plus h okay, for any h, minus f of x is equal to, okay, well, let's just plug it in. It's b times the vector x plus h plus lowercase b minus b times x plus lowercase b. And when you distribute the minus sign and you distribute the b across and then cancel out the lowercase b's, you get that this is equal to b times h. Okay, what does that imply about the differentiability of capital F? We see that f is differentiable at every x in Rm, in Rn. Okay, how do we know that? Because we know, so we want to show that there is a linear function L such that this numerator divided by the denominator approaches 0. But if you define L to be the linear transformation associated to B, then the numerator is just 0, right? Because just take L to be the linear transformation associated with the vector, with the matrix B, and we see that the derivative of f at x is just b. Right, so this would be like saying, in the case where n and m are 1, that if you have a function f of x equals mx plus b, then the derivative at every x is m, right? It's just that m is replaced by a matrix, and instead of the derivative being m, we have the derivative being the matrix B. Okay, so that's the definition of differentiability. I hope that this helped with understanding why we define the definition the way we do, and that in fact it is a generalization of differentiability in the single variable calculus case. Okay, thanks for watching.